Welcome back, everyone. Brazil has entered the global race for clean energy innovation by launching its first research initiative focused on nuclear fusion. This project, led by a collaboration between national universities and energy institutes, marks a bold step toward long-term energy independence. Unlike traditional nuclear fission reactors, fusion reactors aim to replicate the process that powers the sun, using hydrogen isotopes to produce vast amounts of energy without radioactive waste. Brazil's prototype facility will concentrate on magnetic confinement technology, specifically using a tokamak design to test plasma stability and heating methods. Located near São Paulo, the new research site is equipped with superconducting magnets, advanced diagnostics, and control systems to manage the extremely high temperatures required for fusion. This effort represents more than a scientific experiment. It signals Brazil's determination to invest in high-technology infrastructure that could power its cities and industries for generations. The foundation of Brazil's fusion research reactor is based on the tokamak configuration, a donut-shaped chamber where hydrogen isotopes are heated until they form plasma. This plasma, made of charged particles, must be kept away from the chamber walls using magnetic fields. Brazilian researchers are developing superconducting magnets to generate the strong magnetic fields needed to contain and shape the plasma. These magnets operate at extremely low temperatures using liquid helium cooling systems. Without physical contact with the walls, the plasma can reach the conditions necessary for nuclear fusion, where atomic nuclei collide and release energy. The challenge lies in sustaining these conditions long enough for meaningful reactions to occur. Plasma heating in a fusion reactor requires a combination of systems that work together to raise the temperature to tens of millions of degrees Celsius. In Brazil's tokamak system, researchers are experimenting with three primary heating methods. Ohmic heating uses electrical currents passed directly through the plasma. Neutral beam injection sends high-energy atoms into the plasma, where they transfer their kinetic energy through collisions. Radio frequency heating involves beaming electromagnetic waves that resonate with particles in the plasma. These methods are used in sequence or together to raise the plasma temperature to the level needed for fusion reactions to begin. Fueling a fusion reactor involves the precise introduction of hydrogen isotopes, typically deuterium and tritium, into the vacuum chamber. In Brazil's research system, gas puffing techniques are used to inject measured amounts of deuterium into the plasma chamber. For future experiments, the team is also working on pellet injection systems, where small frozen hydrogen pellets are fired into the plasma core. These methods aim to achieve a uniform plasma density and maintain continuous fuel supply during operation. Proper fuel management is essential to prevent instability and ensure that the fusion reaction occurs in a controlled and efficient manner. Magnetic confinement is maintained using toroidal and poloidal field coils that work in tandem to keep the plasma stable. Brazil's engineering teams are designing complex coil geometries that produce a twisted magnetic field around the chamber. These fields counteract the natural tendency of the plasma to drift or escape. The magnets are supported by cryogenic infrastructure that keeps them below superconducting temperatures, which minimizes electrical resistance and allows powerful current flow. Sensors embedded in the chamber monitor magnetic field strength and plasma position, providing real-time data for adjustments. Maintaining precise control of the magnetic field is one of the most difficult tasks in fusion research. Diagnostics are critical to understanding the behavior of plasma inside the reactor. Brazil's fusion reactor is equipped with instruments that measure temperature, density, impurity levels, and particle flow. Tools such as Thomson scattering systems, magnetic probes, and spectroscopy arrays give researchers a detailed picture of the plasma environment. This data is used to validate models, adjust heating methods, and detect instabilities before they grow. High-speed imaging allows scientists to observe disruptions and understand how the plasma responds to changes in magnetic configuration. By studying this data, engineers can develop better control strategies and increase the duration of stable fusion conditions. Control systems in the fusion reactor rely on powerful computing infrastructure to respond to real-time conditions. Brazil's teams are developing software that can interpret sensor input and adjust magnet currents, fuel injection, and heating parameters in milliseconds. These control loops are essential for preventing disruptions that can damage the reactor. The system must detect early signs of turbulence or instability and respond instantly to preserve plasma integrity. Operators use dashboards to visualize data and intervene manually if needed. These systems are constantly refined based on experimental outcomes and are a key element in moving from research to practical energy generation. Vacuum systems are essential for maintaining the low-pressure environment required inside the tokamak. The fusion process must occur in near vacuum to prevent unwanted reactions with air or other gases. Brazil's reactor uses turbomolecular pumps and cryogenic traps to evacuate the chamber before plasma formation begins. These systems must be leak-tight and capable of maintaining consistent pressure throughout the experimental run. The vacuum environment also allows better control of plasma parameters and reduces contamination. Engineers conduct regular leak checks and system purges to maintain the purity and stability of the chamber before each test. Cooling systems serve two main purposes in Brazil's fusion reactor. First, they keep the superconducting magnets at cryogenic temperatures using liquid helium. This ensures that the magnets can operate efficiently without electrical resistance. Second, they remove heat from components that are exposed to high-energy plasma. Water-cooled panels or heat exchangers surround the chamber to carry away excess thermal energy. These cooling loops must operate continuously and respond quickly to changes in temperature. Safety protocols are in place to handle thermal overload or coolant loss. Effective cooling protects the structural integrity of the reactor and enables longer plasma experiments. Safety and shielding systems are integrated throughout Brazil's fusion research reactor. Although fusion produces less long-term radiation than fission, high-energy neutrons can activate surrounding materials. Engineers use layers of concrete, steel, and specialized radiation-absorbing materials to contain neutron flux. The reactor is designed with remote handling tools to inspect or replace components without human exposure. Monitoring stations detect radiation levels, magnetic field strength, and power fluctuations. Emergency shutdown procedures are tested regularly to ensure that the system can be safely powered down in case of malfunction. These precautions protect both personnel and equipment during experimental operations. In the future, Brazil may develop compact fusion systems that serve as power sources for remote regions, industrial zones, or space missions. These reactors could incorporate advanced materials that withstand extreme temperatures while requiring minimal maintenance. Artificial intelligence might be used to manage plasma stability and energy output in real time. With continued success, Brazil could export fusion components or even turnkey systems to other nations. The experience gained from early research could position Brazil as a regional leader in clean energy solutions based on fusion technology. If Brazil succeeds in building a stable fusion reactor prototype, the country could join a very small group of nations leading the development of next-generation power systems. Future scenarios may include small-scale reactors providing electricity to industrial centers or modular systems designed to operate in remote regions of the country. Brazilian engineers are also exploring how this fusion research can contribute to international efforts such as ITER or DEMO, creating opportunities for global collaboration. In the long run, domestic fusion capability could reduce reliance on fossil fuels, eliminate energy shortages, and create high-tech jobs. As development continues, Brazil is positioning itself not just as an energy consumer, but as a future energy innovator. Thank you very much for watching. Please like and subscribe.